Good morning, everyone. Thank you very much for attending the opening session of the second International Conference on Pattern Recognition and Artificial Intelligence. This conference was supposed to take place in Zhongshan City in China. Unfortunately, due to disturbances in Hong Kong and later the onset of COVID-19, we have to move the conference to online. So this is the situation. And we hope everyone is attending and will enjoy the conference. And I would like to introduce the panelists of the conference. Professor Y. Tang from University of Macau. Can you please say a few words, Professor Tang?
Welcome everybody to attend this conference. I hope you have a good time for this conference. Okay?
Good. Not only the conference, but also the concert on the last day. And I would like to introduce Program Chair, Professor Yuan from Baptist University. Can you please say a few words, PC?
Hi, welcome to the conference, and thank you very much for the submission. A very high quality paper. I hope you enjoy the conference. Thank you.
Very good. And actually, I should introduce Conference Secretariat, Nicola Nobili, who has been working so hard to make this online conference possible. And, normally, we'll start at 8 o'clock in the evening, Hong Kong time. That is 8 o'clock Montreal in the morning, and 2 o'clock in the afternoon in Paris. And we finish the day after about 3 hours. That is to say, we have 2 keynotes, one at the beginning and one at the end, and technical sessions in between. So we'll try to hold that pattern. The concert will be exciting and so on Friday, the 23rd. So without further ado, I would like to invite our honored guest to open the conference, Professor Roland Ching, President of Baptist University, who had been working on image processing many years ago, that I started to communicate with him. Subsequently, he took on senior posts in University of Science and Technology of Hong Kong, University of Hong Kong, and presently the presidentship of Baptist University. He is also an advisor of the Journal of Pattern Recognition. Professor Roland Ching, it's our honor to have you to open the conference. Professor Ching.
Okay, thank you. Thank you, everyone. Thank you, Ching. It's nice to see many names that I know and some new friends I don't know. And Professor Ching just mentioned that there are 150, 160 registration, which is very good considering the situation. So first of all, let me formally open this particular conference, 2020, ICPRAI. Welcome you all to this special event. And we are here to share research outcomes and exchange ideas in the next few days. This is indeed exciting. These exciting ideas and research findings are a great deal of inspiration in this midst of this new normal. Everyone now is living in this new normal under the threats of COVID-19 pandemic and also the worldwide geopolitical tension. These two things has been bothering the world for the past year or year and a half. COVID-19 has caused serious disruption around the world. We have loss of lives, loss of jobs, to our sense of insecurity towards the future. The future, perhaps 1 year, 2 years, 3 years, no one knows. On the other hand, the geopolitical tension at the international, regional, and local levels have also put us on edge, as if a Cold War is looming in the horizon. This sounds very, very gloomy. But when I look at the program, which I have a copy of here in my hand, when I look at the exciting programs with researchers from around the world, and your enthusiastic participation in this conference, as Mr. Ching mentioned, 150 participants, I see a silver lining. Hardship must have inspired innovation. Perhaps everyone has no entertainment, nowhere to go, and stay home and do programming and do research and write papers. So that is a welcoming effect of this pandemic. All our conference participants are innovators and pioneers in this field. And this conference has shown their creativity and commitment to their advancement. I wish to thank everyone who has come together in this new normal to advance our common interest in AI, pattern recognition, image processing. I wish you a very successful conference, and I look forward to listening to some of the talks. I will be in and out of the conference in the next few days, hopefully to learn a few things. And again, thank you very much, and then have a successful conference. Thank you.
Thank you very much, Professor Chen. And now we'll start the keynote speech. And we have 8 keynote speeches. Except the first one, the keynote speaker cannot come. All 7 other keynote speakers, 7 plus 1 actually, will be live, presenting their talks live in person. So right now we'll start the talk by Professor Xiaohuan Li, who is the president of the Korean Society for Artificial Intelligence, and has been very successful in research on brain computing. So he will talk up on that subject, and he has provided a video.
Thank you, Mr. Chairman. I'm very honored to give a talk in ICPRAI conference. The topic I'm going to talk today is brain-computer interface.
Thank you so much. It's so fantastic here in Seoul and in Korea. And I've been really inspired by the work that is happening with Professor Lee in the Korea University. One of the things that Professor Lee is doing is really saying, okay, let's take the latest breakthroughs in the brain-machine interface. It's literally building a statistical model of your brain activity or your intent, and turn that into control for your prosthetic arm or a robotic arm.
As shown in previous video, brain-computer interface enables the control of external devices only by their thoughts. In other words, it is a communication system that interprets and delivers the user's intention to the external world without relying on the muscles. Many BCI research projects are going on around the world. Typing by project of Facebook aims for typing 100 words per minute using brain signals. Also, human AI hybrid project by Neuralink, owned by Elon Musk, aims for developing BCI communication to connect humans and computers based on AI. They are currently developing brain chip to detect human states in real time. BCI research is also actively underway in the automotive industry. Nissan is developing a self-driving technology to read the driver's intentions using brain signals. There are two main ways to measure brain signals. One is the invasive method of acquiring brain signals by implanting electrodes directly into the scalp. The other is a non-invasive method of acquiring brain signals from electrodes on the scalp. The non-invasive method has the advantage of being safe and easy to wear. For example, there are fMRI, MEG, and EEG as representative tools. Among them, EEG is suitable for real-life applications. EEG stands for electroencephalography and was first measured by German physiologist Hans Berger. As the brain becomes active, the flow of electricity between the nerves of the brain is measured by electrodes attached to the scalp. Let me explain how BCI system works. The first step is to measure EEG signals on the standard coordinate system as shown on the left figure. Different brain states are active in different regions as depicted on the right figure. Therefore, the second step is to learn the activation patterns for specific brain areas. By using these patterns, finally, we can predict the user intention based on machine learning techniques. This is a homunculus, which manifests the reason why the brain signals enable to control devices. A cortical homunculus is a distorted representation of the human body based on a neurological map of the brain areas. The blue regions represent the somatosensory cortex, whereas red regions represent the motor cortex. For example, the brain area associated with hand takes over a large area because it has to perform sophisticated movements. There are 6 major BCI paradigms. The first paradigm is motor imagery. For example, when you imagine moving your left hand, the brain signals related to left hand movements are generated over the right motor cortex. The second paradigm is event-related potentials. This is the brain signals generated after being presented to some target events. For example, a P300 potential is a large positive deflection that peaks around 300 milliseconds after presenting target stimuli. The third paradigm is movement-related cortical potential. The MRCP paradigm induces the low-frequency signals generated by the planning or execution of voluntary movements. These signals are generally occurred in motor-related brain regions such as supplementary motor area and primary motor cortex. The fourth paradigm is the steady-state visual evoked potential. In this paradigm, the brain signals are induced during concentration on a particular visual stimulation. Spectral features of the brain signals are increased on the occipital lobe by the visual stimulus. Therefore, different frequencies of visual stimulation can be used as various commands of BCI. The fifth paradigm is steady-state somatosensory evoked potential. When the users concentrated on a particular vibration stimulation, some specific brain features are generated. The sixth paradigm is imagined speech. which is a signal that occurs when you imagine speaking without making a sound or moving the articulators. Language-associated brain areas over the temporal lobe is activated during the imagined speech. Specifically, Broca's area is related to generating language, whereas Wernicke's area is related to understanding language. As you can see on the table, there are various types of speech associated by whether it involves voice output or actual motion of the articulators. From now on, I would like to briefly introduce the recent research activities in our lab. We have mainly focused on the non-invasive BCI paradigms. Okay. First, we developed a lower limb exoskeleton control system based on SSVP. The exoskeleton robot may help patients with mobility difficulties and can further be applied for the exosuit technology in the future. We proposed brain signal processing algorithms for robust decoding under ambulatory environment. The proposed CNN-based exoskeleton control method outperformed the conventional method. The feature representation displays the target stimuli frequency components that the network focused on. Based on our research, we could demonstrate the feasibility for the real-life applications. Let me show you demo video.
Transform their lives. When used in combination with an exoskeleton that enables movement, the brainwave interface measures EEG signals and then decodes them into motion control orders. Professor Lee Sung-Wan and his team at Korea
The exoskeleton robot reads the brain waves of the user and removes unnecessary external noise through the signal processing system. Then, the robot picks out and classifies the certain characteristics of the brainwave to the designated orders.
To do that, a visual stimulus generator is used to read the brainwaves. The device has 5 LEDs that represent different commands, such as turn left or right, walk forward, stand. Each of these commands has a different frequency, so the corresponding LED light flickers when a signal is sent.
When a user focuses on visual stimuli, the same frequency is generated in the occipital lobe of the user's brain.
The control system collects the signals with the EEG cap through a wireless transmitter receiver and converts them into system instructions to operate the exoskeleton. While the system is focused on helping the disabled become more mobile, this technology will be applied to other devices, including self-driving cars and self-navigating drones.
Project was to develop a robotic arm control system to decode various upper extremity movement intentions. In particular, we used intuitive thought for performing high-level tasks such as drinking of water or moving some objects. By using the large EEG database, we developed the brain-controlled robotic arm system to conduct high-level tasks. We proposed a multi-directional CNN bilateral short-term memory network based on robust decoding of intuitive upper limb movements. Let me show you demo video.
Pen paste. Water.
The conventional scalp EEG is less convenient and takes 30 minutes for the experiment setting. Therefore, the ear EEG has recently come into the spotlight. This is convenient and user-friendly, which is much more suitable for real-life use. Then, how can we measure brain signals over other areas using only the signals around the ears? We proposed the novel regression method to estimate EEG signals in the visual and motor area. We proposed an error correction regression framework which can estimate the ear EEG signals in other areas by correcting estimated errors. The classification performance was increased by more than 10%, from 80% to approximately 92% before the application of the technology. In addition, we also developed biocompatible and multiple porous semi-dry electrodes for EEG monitoring. The advantage of this technology is that it automatically forms a stable conductive interface when the electrode is attached to the scalp. These electrodes do not use a conductive gel, so it is clean, biocompatible, and easy to use. And the electrodes can measure stable EEG signals for up to 20 hours. These are the results of the proposed electrodes. The electrodes measure the high-quality EEG signals with very low impedance of approximately 7.6 kilo ohm on the scalp with the dense hair layers. In addition, the electrodes maintained a very low impedance compared to conventional electrodes in the long-term EEG signals monitoring experiment of 8 hours. One of the key functions of BCI is to enable communication with external world only with the brain signals. BCI speller system is the most widely used BCI communication method which enables typing with brain signals. Conventional BCI speller systems such as event-related potential speller, steady-state visual evoked potential speller, and motor imagery speller have shown robust performance in conveying the user's intention. However, these conventional BCI speller systems hold crucial limitations of relying on external stimuli and requiring display equipment for selecting the characters. This is because they operate with brain signals induced by external stimuli or brain signals unrelated to the language. Current BCI systems are orienting towards an intuitive system that users can operate easily. Since the conventional BCI communication system brings up issues of non-intuitiveness and conversation irrelevance, intuitive BCI communication based on speech-related BCI paradigm is recently gaining attention. Imagined speech is the emerging paradigm for an intuitive BCI communication that can directly convey the user's intention. It is an intuitive BCI paradigm since speech is a natural and most widely used form of human communication. From now on, I would like to briefly introduce the recent research activities in our lab. We named our work as BTS, which stands for Brain-to-Speech. In other words, this technology is to translate the user's imagined speech into a voice output. Intuitive BCI communication is possible just by imagining the very thing that the user wants to say. Here is recent work on speech reconstruction based on invasive brain signals.
Shipbuilding is a most fascinating process.
Shipbuilding is a most fascinating process.
The proof that you are seeking is not available in books.
The proof that you are seeking is not available in books.
We constructed a large database of imagined speech along with the spoken speech. 16 subjects participated in this study. In the imagined speech session, subjects were instructed to imagine pronouncing the clock after hearing the cue audio of clock. In the spoken speech session, subjects spoke out loud after hearing the cue audio. We used the audio of 12 words for the cue. 12 words contain 6 concrete words that have a specific form and 6 abstract words without specific form. We observed common features of imagined speech and spoken speech. We found speech-related potentials that have shown significant correlation between imagined speech and spoken speech. As you can see in the left figure, positive peak near 600 milliseconds from the onset and the negative peak near 1100 milliseconds was mainly found. Also, common spatial patterns of imagined speech and spoken speech have shown similar distributions between each other. The common spatial patterns of imagined speech have shown widely distributed patterns over sensory motor and the temporal areas. Importantly, we found ERD-ERS patterns focused on the left frontotemporal area, which is related to speech production. The classes with low true positive rate had shown a relatively weak activation patterns on the temporal lobe. For the intuitive BCI communication, we compared the results of imagined speech with another intuitive paradigms, visual imagery. We classified the aforementioned 12 words into a total of 13 classes, including a rest state class. The 12 words contained vocabularies that are frequently used for patients' conversation. Our classification performance outperformed the confidence boundary in both the imagined speech and visual imagery. Also, the binary classification accuracy was maintained when only using the channels from relevant brain regions. We are currently working on applying the transfer learning to improve the imagined speech classification performance. We extracted the common features of imagined speech and spoken speech included in the high-frequency activation. Therefore, we are developing a domain transfer learning-based feature analysis technology optimized for the imagined speech classification. Let me show you the demo video of our imagined speech classification works.
Tom, help me.
I'm here. What can I do for you?
How's the weather today?
Look, it's sunny today. Do you need any more help?
Please turn on the TV.
Okay.
Beyond the classification issue, we developed a speech synthesis technology that reconstructs imagined speech using brain signals. We adjusted our BCI technology with current sentence level speech synthesis technology based on feed-forward transformer network. Our model could reconstruct spoken speech using the EEG of spoken and silent speech. These are the audio of original and reconstructed speech.
저는 서천들하고 아주 가깝게 지내요. 저는 서천들하고 아주 가깝게 지내요. 저는 사천들하고 아주 가깝게 지내요.
We are also working on adjusting our BTS technology on brain signals of imagined speech. Speech synthesis with spoken brain signal have shown possibility of successful BTS system. However, previous works are limited on invasive brain signals of spoken or listened speech. As I mentioned before, the imagined speech does not have proper speech audio and onset for the ground truth. By using the similar aspects between the imagined speech and the spoken speech, we are investigating the issues of imagined speech-based BTS system. The demo video of our brain-to-speech synthesis technology.
여기에서 가까운 곳에 서점이 있나요? 가까운 시일 내에 한번 댁으로 찾아가겠습니다. 범인은 20대 중반에서 후반의 남성으로 보입니다. 모든 게 궁금해. 여기에서 가까운 곳에 서점이 있나요? 거기 자주 가는 곳에 서점이 있어요. 범인은 20대 중반에서 후반의 남성으로 보입니다. 범위를 50대 롱다에서 꿀판을 단서도 보입니다.
BCI technology is growing rapidly with the development of artificial intelligence. Let's wait and see the development of better technology in the near future. For further inquiries, please send email to me. Thank you for your attention.
Thank you very much, and we appreciate very much the video presentation. And so any questions, please direct to Professor Lee with the email address on the screen. And now we'll start the technical session. The first session has to do with the handwriting and the text analysis. So Nicola will introduce them. Some will be live presentations and some will be videos. And due to time constraint, each presentation will be about 10 or less minutes. Nicola, please say something and introduce the speakers.
Okay, well, for session A, handwriting and text processing, we have one live presentation by Najla Alqawasmeh. Her talk will be on gender detection from Arabic handwritten documents using the concept of transfer learning.
Okay. Hello everyone. Good morning. I hope you are all in a good health. Just a minute. Let me start by giving you the general outlines of my presentation. First, I will give you a brief introduction about gender detection. Then I will briefly talk about the previous works in the literature review section. I will also talk about the limitation and objectives of my research. After that, I will explain in details my research plan and methodologies regarding the 4 main phases of automatic handwritten analysis system. Finally, in the summarization section, I will conclude the main points of my presentation. In the next slide, I will talk briefly about handwriting analysis. Handwriting is commonly known as brain writing because the writer can control what to write but not how to write it. Therefore, handwriting is a mirror reflecting the writer's personality and emotional outlays. Handwritten analysis is a powerful tool that can be used in many sectors where people interact, such as recruitment, management selection, forensic application, writer identification and verification, personality profiling, and social network analysis. If we want to talk about the history of handwriting analysis, we can say that it is not a new research topic. The beginning of the interest in graphology goes back to 400 years. In our research, we worked in forensic graphology, where the analyst should be able to figure out the writer of the handwriting and in which condition the text was written, such as in laying or standing, ill, or under a lot of stress. Gender detection is a biometric and forensic application, as gender can be detected from different biometric features such as physiological traits or behavioral traits. It is a vital research area in many sectors, including psychological studies, document analysis, writer identification, and forensic analysis. In the forensic domain, it helps to limit the investigation to a limited category of population, as processing each one of these categories separately leads to improved results in writer identification. Interest in gender detection began many years ago, where in 1999, Huber and Hedrick presented the correlation between handwriting and several categories, including age, handedness, and gender. Many researchers developed an automatic gender detection system by extracting different set of features, such as Al-Ma'adid and Hussein. They extracted geometric features from handwritten, and they got 74.06 of gender classification accuracy. One of the biggest challenges in the handwriting analysis system is the lack of label databases to enable active innovation. Another challenge in our work is dealing with the Arabic language because of a range of challenges that characterize Arabic than other languages, including the dotting, direction of writing, the diacritics, and the connectivity features. Also, the high similarity in the handwriting between people is a big challenge in our work, so we put a considerable effort to set the most discriminative gender-related features to get a high classification rate. In this study, we aim to provide a system that overcomes all these challenges and developed a powerful gender detection system from handwriting. The manual detection process of gender is expensive, tedious, and exhausting. This makes the automation of the detection system important. In our research, we will focus on automating the writer's gender detection system from handwritten documents. Collecting and labeling a good data set for training and testing any classification system is one of the most important steps to achieve a good performance, as the performance of handwritten classification system is highly dependent on the extracted features. We worked on developing an automatic feature extraction method. In our proposed method, we used 2 well-known CNN architectures, GoogleNet and ResNet, for the detection and the classification of the writer's genders from his or her handwriting. We use the extracted features from each network individually, and then we fit them to an SVM classifier. This figure shows the general structure of our proposed method. The performance of such systems should be evaluated using a large data set that includes hundreds of documents written by different writers. For this purpose, I collected my own data set where first I asked the volunteers to fill out an information page that includes gender, age, hand used, and job. Hence, data set should be large enough to cover all the different handwritten styles. We asked 2,200 volunteers to write a letter for someone they love. We also asked a portion of the volunteers to copy some paragraphs for future research purposes. Our data set was collected from several places such as universities, schools, companies, and some restaurants. The variation in the educational levels of the participants is also interesting. The data set was written not only by highly educated people, but also by less educated people. The volunteers included elementary school students, secondary school students, and university students, as well as worker, employees, engineers, doctors, professors, accountants, and secretaries in industrial. The age of the volunteers range from 12 to 70 years old. The data set was 65% written by female and 55% written by female and 45% written by males. Most of the volunteers are right-handed, except 3 to 4 are left-handed. In total, the data set contains 2,700 digitized pages. They were written in Arabic and English by 2,200 writers. No restrictions was put in the type of the pen used in writing. What distinguishes my data set from other available data sets that it has the highest writer number, which gives a higher diversity in the handwriting samples. As you can notice here, our data set is the highest in the writer number. And these are some samples of our freestyle handwritten documents. The next step in our proposed system is processing, where the pre-processing in our research is mainly the resizing of the images to the appropriate size related to each pre-trained network. For example, ResNet, the images resized to 223 by 223, and for GoogleNet, the images resized to 227. In the feature extraction phase, the most relevant information is extracted from a raw data and represented in a reduced set of features vectors. The performance of the classification system is highly dependent on the extracted features. In our automatic feature extraction method, we use transfer learning, as transfer learning is used to speed up and improve training in a new task using the knowledge of a second trained task. We applied the concept of transfer learning using 2CNN architecture, as mentioned earlier, as fixed feature extractors from the handwritten images. These CNN architectures have been trained over 1 million images from ImageNet, and they can classify images into 1,000 categories. We replaced the last layers of each pre-trained network, GoogleNet and ResNet, with the new fully connected layers adapted to our dataset. The new final layers can extract features that are more relevant to our target task. Then we specify the number of classes in our dataset, which are female and male. We also kept the weights of the transferred layer, the early layers of the pre-trained networks unchanged by setting their learning rate to 0, but we increased the learning rate of the new fully connected layers to speed up training and to prevent overfitting to our dataset. We evaluated our proposed approach using 75% of our dataset for training and 25% for testing. SVM method was used to analyze the extracted features and classify the writer gender into female and male. We got a high performance of 83.32% of accuracy when we used the ResNet with its powerful shortcut connections, while the performance of the GoogleNet was equal to 80.05%, as the use of a bottleneck layer 1x1 convolutions helped in the reduction of the computation requirements. We got an accuracy, sorry for that. In this section, I will sum up the main points of my work. We have prepared a new data set of Arabic handwriting for different research purposes related to human interaction. Transfer learning concept was applied for gender detection using 2CNN architecture, ResNet and GoogleNet, and we got 83.32% and 80.05% for both networks respectively. Thank you.
Hello everyone, my name is Jiashu Huang from Sun Yat-sen University, China, and today I'm honored to be here to report. My topic is Overview of Mathematical Expression Recognition. As we know, mathematical expression, ME for short, plays an important role in scientific and technical documents, and ME recognition has been one of the most fascinating research among the various researches in field of image processing. This paper firstly discussed the three major problems of ME recognition, including symbol segmentation, symbol recognition, and structural analysis. Then, introduced the research status of ME recognition from document images or handwritten forms. Finally, we look forward to the future development of recognition of ME. The first part is the major problem. In symbol segmentation, the mathematical symbol system is a symbol system with two-dimensional spatial layouts, which is different from the traditional narrow language texts with only a single sequence in the horizontal direction. For example, an expression includes a semi-enclosed structure composed of a root number and a square number. A fifth integrator operation includes an integrator and an integral upper and lower limits. In symbol recognition, local ambiguity is an unavoidable problem. Local ambiguity means that the specific content represented by some strokes is difficult to distinguish, especially in handwritten things. For example, as you can see, the handwritten English character O and the numeric character 0 are difficult to distinguish. Meanwhile, the character set of mathematical symbols are quite large, including English letters, Roman letters, Greek letters, numbers, and many other operators. At the same time, font, size, bold, italics, and others makes the recognition of mathematical symbols more complicated. For example, in printing, the italic English letter A and the flower font A are difficult to distinguish. In structural analysis, depending on the spatial operator, include implicit multiplication, power, or subscript. ME has the unique two-dimensional structure, which makes the spatial relationship between symbols more complicated. This figure shows the same configuration of bounding boxes may indicate different spatial relationships. The next part is the research status. In the field of document recognition, Hart et al. Proposed a recursive XY cut segmentation method, which worked well on typeset MEs, but however not fitted for handwritten cases. Kumar et al. Tried a rule-based approach in symbol information step by assuming connected components of a given labeled ME image. Kim et al. Proposed a modified recursive projection profile cutting method of a character segmentation in image of ME using depth-first search for arranging and double-linked lists for rearranging. Muru et al. Used ANN in order to develop pattern recognition algorithms, which is capable of recognizing both normal texts and ME, and presents an original improvement of the backpropagation algorithm. In field of handwritten recognition, Hirata et al. Proposed an approach based on expression matching for generating ground truth examples of expressions. Matching is formulated as a graph matching problem. McLean et al. Presents an approach for parsing two-dimensional input using relational grammars and fuzzy sets, motivated by the two-dimensional structure of written mathematics. A fast, incremental parsing algorithm is developed. At the same time, they also use Bayesian networks for parse tree selection as another approach. Samitier et al. Simplified the elastic template matching distance based on the directional feature of the pen. The symbols are then sequentially analyzed using six spatial relations. Alvaro et al. Describes a model using two-dimensional stochastic context-free grammar and the hidden Markov models to identify online handwritten MEs. While et al. Handles ME recognition as a simultaneous optimization of expression segmentation, symbol recognition, and two-dimensional structure recognition under the restriction of a mathematical expression grammar, which is a global strategy. Hu et al. Using dynamic programming in symbol segmentation, using a Gaussian mixture model learned through expectation maximization in symbol recognition, and using a ternary tree in semantic relationship analysis module. And for about narrow work, Lei et al. Proposed a system with three parts: a convolutional narrow network for feature extraction, a bidirectional LSTM for encoding extracted features, an LSTM, and an attention model for generating target lattice. They also modified the recursive XY cut method in order to normalize the stroke order. Ting Zhang et al. Extend the chain structure BLSTM to tree structure topology and apply this new network model for online ME recognition. The proposed system addresses the recognition task as a graph building problem. Jiashu Zhang et al. Introduced track, attend, and parse TAP, an end-to-end approach based on narrow network. The architecture of TAP consists of a tracker and a parser. The tracker employs a stack of bidirectional recurrent narrow networks with GRU to model the input handwritten traces. The parser adopts a GRU equipped with guide hybrid attention GHA to generate lattice notations. And finally, we look forward to the future. Through the efforts of researchers, recognition technology is becoming more and more mature. The three problems we mentioned earlier can solve separately or jointly. In the past, due to technical and computational limitations, researchers perform separate calculations for each step. With the development of computing power and algorithms, more and more research attempts to solve the problems from a global perspective. In the future, depending on the full development of computing power, the application of deep learning for research may have good prospects. In global recognitions, the algorithm can try to make full use of the context information and can be continuously improved in network design or loss function. And that's all of my report. Hope to learn with all of you. Thanks for your time.
Hello everyone, my name is Fukeng He. Today I'm going to introduce my paper in ICPRAI 2020, Handwritten Mathematical Expression Recognition, a Survey. The authors of this paper are me and my teachers, Jun Tan and Ning. We are all from Sun Yat-sen University. First of all, I would like to introduce handwritten mathematical expression recognition, abbreviated as HMER. Handwritten mathematical expression recognition is one of the most difficult topics in OCR due to the ambiguity of handwritten mathematical symbols and mathematical structure. It can be applied in many different areas, like scientific document recognition and education. Usually, HMER can be divided into two parts, online handwritten mathematical expression recognition, abbreviated as OHMER, and offline handwritten mathematical expressions recognition, abbreviated as OFHMER. OHMER studies the model that maps the input point series into LaTeX code, and OFHMER proposes a model to map a static figure into his LaTeX code. HMER typically includes three major steps, that is, stole segmentation, single symbol recognition, and structural analysis. However, papers that provide literature survey of the area of handwritten mathematical expression recognition research are rare. So, in this paper, we present a review on the development path of handwritten mathematical expression recognition. Secondly, handwritten mathematical expression recognition is a difficult topic for the following three reasons. One is symbols and characters are rendered in a complex two-dimensional structure. And two is recognition of single symbols is difficult due to the enormous ambiguities in handwritten input and strong dependency of contextual information. Structural analysis is also a difficult step because of the ambiguities in the spatial relationship of each symbol. For example, in the figure on the right, it is difficult to distinguish G and 2 directly in A, but it can be inferred according to the context, like 1.23. Besides, in B, there are two kinds of judgments. One is X, and the other is two blankets. Thirdly, traditional methods include sequential solutions and global solutions. Sequential solutions first segment input rows or input static figures into single mathematical symbols and recognize them separately. The analysis of two-dimensional structure is then carried out based on the best symbol segmentation model and the best symbol recognition model. Global solution integrates symbol segmentation, symbol recognition, and structural analysis, but they are computationally expensive. Fourthly, neural networks have achieved high performance in many areas of OCR like syntax recognition, handwritten text recognition, so no surprisingly, neural network can be applied to mathematical expressions recognition. Neural network-based methods can be applied in it. There are two kinds of neural network-based methods. One is sequence-to-sequence method, and the other is tree-based method. Encoder-decoder has been exposed to address sequence-to-sequence learning. The encoder-decoder is designed to handle variable length input and output sequences. Such a framework has been applied extensively to many applications, including machine translation and speech recognition. Handwritten mathematical expression recognition can be seen as a sequence-to-sequence problem. Jun proposed an end-to-end neural network-based handwritten mathematical expression recognition system using a sequence-to-sequence network with attention mechanism to encode the figures into high-level representation using CNN and decode them into the target lattice sequence using INN. This method is data-driven and doesn't need any predefined grammar. It alleviated the problems caused by symbol segmentation and computationally demands of employing an ME grammar. Followed by the paper above, Jun presents a neural network method for online handwritten mathematical expression recognition. This paper proposes a sequence-to-sequence network with attention mechanism named GHA to transform the X and Y coordinates of the strokes into lattice sequence. Since any mathematical expression can be expressed as a tree form, so tree-based recurrent methods can be utilized to mathematical expression recognition. Tin Zhang proposed a method based on the tree-based method. It has no explicit segmentation, recognition, and layout extraction steps, but a unique trainable system that produces directly a stroke label graph describing a mathematical expression. In this paper, tree-based BLSTM framework is used to transform the input strokes into the target lattice sequence, and this new work is trained with CTC laws. With the development of the pen-based device, we already have all the necessary hand aware for entering the mathematical expressions into the computer in offline form or online form. However, the recognition accuracy of mathematical expression is not satisfactory, with the state-of-the-art accuracy less than 70%. Therefore, this field is very potential in OCR and more research is needed. Moreover, with the development of neural networks methods like CNN or NN, deep learning method is utilized in both the offline and online mathematical expression recognition. These methods are end-to-end methods without explicit segmentation, recognition, and layout structure extraction steps. Besides, they are data-driven without predefining the grammar of the mathematical expressions, so they have advantages in mathematical recognition. Thank you for listening.
The next session, session B, is about features and classifiers. So our first live presenter will be Chun-Lei He, and she'll be talking about a hybrid multiple classifier system applied in life insurance underwriting.
All right. So good morning and good evening, everyone in the world. So my name is Chun-Lei, and I'm Dr. Suen's PhD student, graduated 10 years ago. So I'm now a lead data scientist and director of data science in Canada Life. And so I would like to happy to present my paper, and it's called Hybrid Multiple Classifier Systems Applied in Life Insurance Underwriting. So So this is the agenda. So I will follow from introduction to a hybrid multiple classifier system, including from data pre-processing and the feature extraction, classification, rejection criteria, and eventually have the conclusion and business impact. So first thing is this paper applied to the underwriting in life insurance. So first thing is, what is the definition of underwriting in life insurance? So this is a procedure to measure the risk exposure and determine appreciate rate class in life insurance. So that's really a complex procedure that's involving underwritings from different levels, from junior to director, and also including medical consultants and risk teams and pricing teams and so on. So business come to us and to data scientists and to talk to us and say, this is a really traditional way of doing underwriting, 100% manual. And they're facing a lot of challenges, including timing. Every case average of the processing going to be around maybe 10 days and eventually get a conclusion. Some are even longer, maybe a month. And so that also the cost, just thinking from the underwriters and application, everything, and that's really costly. And the third one is complexity. And that's involving so many people and so many factors and make a final decision. So then they come to a data scientist, and then we realize that's really a problem with the pattern recognition or AI can help. So what do we do? And what we did is propose a novel hybrid multiple classifier system to automatically make underwriting decisions. Actually, this is really classification problem like in AI, and also we can do it in real time. So that's still like traditional way. We need to see our data first, talking to the business and see the data and do the feature extraction and classification. First thing first. So they mentioned they have 3 classes and 3 decisions. That's based on different risks. So we have low, medium, and high risks. And what the data is available to the data scientist. And we can simulate the underwriters. What the data is to them as the application forms. That's including like information about like personal and family medical histories, applicants' demographic information, financial information, occupation and behavior information, and so on. So simply can make decisions based on this. And then we can, we say, just welcome all the data, come to us, and we want to make a decision. And also as a data scientist, we realize, and we have something beyond the underwriters. What's that? Like we can generate the features, some extra features. We don't want to generate in random. And we talk to business and realize, for example, and the BMI, just consider this is a ratio of height and weight. So, but it's also different to people who is 20 years old to 60 years old. So that means age associated with BMI should be some features, but underwriters never consider or they can't find this in their menu. So as a data scientist, what we can do is generate features based on their business meanings. And also we can find some external data source, some open data source or some maybe from certain vendors. And based on their demographic information, we know like people living in downtown Toronto, probably not the same as people who is in urban. So these features we're going to extract together and as feature engineering, massage them together, build our own classification problem. So the next step is classification. So probably people think, okay, so we want to make a decision with 3 classes. Let's just apply a classifier. Yes, that's my first step as well. But then I realized, talk to business, what they need. They need a really, the system is accurate as human beings. They expect to replace somehow in a certain way of human beings, human underwriters. So that's extremely high performance. Mostly like in industry, the data is really, real data is really noisy and kind of dirty. So it's really hard for us to make a really super high accuracy. So then also talk to business, I realized false positive is very expensive. What's that mean? So if we have a case within a low risk class and we predict as high risk class, seems okay. But the opposite way is really different, totally different scenario. So if we have a really high risk class case and predict as low, and we're going to have a really high cost and loss in industry. So we need to customize all these factors together to make this a real application in industry. So what we do, we still use one classifier to make decisions, but we don't trust it 100%. So if this classifier say, yes, that's a low risk, and probably we will need to move these cases to the second classifier layers. That's including quite a few classifiers, do a combination. Like we have quite a few experts just voting. What we want to do, like we only concentrate on the low risk cases, and only do the predictions from that way. And if that's really high classes, high risk, or we have no confidence on the cases, we reject them to the real human beings, the underwriters, that make the traditional manual work. So with this way, and when we use multiple classifier systems, and with total actually we'll have 5 classifiers, and to make final decisions. And also, if we have no confidence, like enough confidence on all these 5 classifiers, and we reject to underwriters. So rejection criteria is super important in this application, because we want to make a decision rely on rejection. If we can't do it well, reject. And so what we do, and because we have total 5 classifiers, and every classifier give us the output, and we also need to make decision rejection or not. So this is also another applications considered as classification. So what we do is we use criteria for rejection is use LDA, linear discriminant analysis. So this is as a measurement for rejection. Actually, this is my work, like my PhD work, part of my PhD work together with Dr. Suen and Dr. Lam 10 years ago. So I leverage what I did in my PhD and to this rejection criteria and use this one. And here's the formula. If anyone have interest on this in details, and you can read the paper. And here, just due to the time, and I just show us this way. And simply you only see this one as just consider the prediction result from the highest, like the top 1 class, the classifier as G1 and the others as rest. Just want to do classification with LDA. Eventually, we can apply this to the rejection criteria. So probably what you see now, I will go to the conclusion directly. Probably see we don't have the result section, because this is really coming from industry application, and they don't allow us to have to publish the result. But what I can tell you here is, as a result, and in this application, like in this system, and we can do, if we simulate like 92% of human beings accuracy, the rejection rate is 20%. That means we accept 80% of the cases. We can do as good as human beings. And also we do a conservative way is if we reject 50%, and we can have 97% of precision. That means even higher than human beings. So eventually this can become to a real project on production. Now it's already 4 years, really profitable. So what I want to conclude here is not just show everyone how I applied my PhD study, like my research work, and also effort to to the industry. I also want to everyone just consider this as an example of the right way to save the cost and improve the efficiencies in industry. And also from here, we can see AI technology is taking industries by storm. So transferring the existing research innovation in AI to profitable products in industry is crucial. And also this HMCS dramatically reduced turnaround time for many of our customers' applications. And also, I think this is also encouraging in industry. Like in my company, they want to invest a stronger future and to help make the insurance company a place where customers want to do business and people want to work. So the final result is this HMCS was the first Canadian life insurance provider adopting AI decision algorithms for underwriting. So that's my presentation. Thank you, everyone. Thank you, Nicola. Thank you, Dr. Sun.
Thank you, Chun-Lei. Hunza sent you a question.
Nice.
So from Lily Liu.
Okay, so let me, I don't know if everyone can see my screen. And for secondary classifier, they trained separate or updated with the, yes, all the classifiers trained separately. Only once we do scoring or prediction and we do integration.
Okay, are there any other questions?
No.
Our next presenter, Dipayan Das, and he'll be discussing analysis of multi-class classification of EEG signals using deep learning on Muse dataset.
All right. So, hello everybody. First of all, I'd like to start with a very deep gratitude to the organizers of this conference that they have managed to come this far even in this hard time of this pandemic. And I'm going to start with introducing myself. I am Dipayan Das. I'm from the Department of Electronics and Communication Engineering from National Institute of Technology, Durgapur, India. And I'm going to present this paper of analysis of multi-class classification of EEG signals using deep learning. This work has been jointly done by myself and Tamal Chowdhury from Department of Electronics and Communication Engineering, National Institute of Technology, Durgapur, India, and Umapada Pal, Sir, Professor, Computer Vision and Pattern Recognition Unit, Indian Statistical Institute, Kolkata, India. Okay, so in this presentation, I'm going to cover the motivation behind our work, the major contribution, the dataset that we used for this, the pre-processing stages involved, the methodologies that we experimented with, and finally the results and analysis followed by the conclusion. Okay, so my work is quite coherent with the first keynote talk that we had today regarding the brain-computer interfacing. So EEG provides a very easy and non-invasive method for brain-computer interfacing, as we saw in our keynote speech today. And apart from that, EEG features are highly correlated with the current state of the brain. So any kind of mental activity can be well seen on the features, EEG signals that one measures using the EEG headbands, or whatever device they're using. Apart from that, EEG signals also help deciphering brain functionalities like emotion, intelligence, and cognition. And this field of EEG has an immense potential for medical applications, specifically in the cases of people who are in coma for a long time, so that they can communicate with their families and the medical personnel. So in this work, we mainly cover the paradigm of digit classification using EEG signals, which was recorded using a Muse headband. So Muse is basically the company and the company of the headband, and the dataset is a publicly available dataset. And we devise a deep learning system that mainly comprises of two parts. One is the feature extraction, which is comprised of the discrete wavelet transform, and second is the two-dimensional convolutional neural network, which we made from scratch. So our pipeline outperforms the existing state-of-the-art results, and we also provide a vivid ablation of multiple other methodologies that we experimented with, which I'm going to cover in some coming up slides. So coming to the brief synopsis of the dataset, the dataset that we used was actually recorded from a 4-electrode headband, which is TP1, TP2, AF7, and AF8, and the positions of the electrodes can be well seen in the diagram on the right. The signal durations were mainly for 2 seconds, and the sampling frequency was around 220 Hertz. The number of samples in each class was around 3,000 for most of the classes, and we had an extra class of which is denoted as -1. It was basically the control class that said that it didn't contain any other classes, so it was basically noise. So the preliminary pre-processings that we performed were mean padding. So this was required because most of the signals that we used were not of the same length. So in order to fit a machine learning algorithm like LSTM or any other models, we had to make all the sequences reach a uniform length. So we padded all the shorter sequences with the mean values of that sequences. Next, we came to the normalization, and we used a min-max scaling scheme to do the normalization of the EEG amplitude values. Then we performed a low-pass filtering using triangular moving average filter, and this was mainly done in order to remove the high-frequency components which correspond to most of the times noise. And lastly, we performed downsampling because most of the sequences were of lengths around 500 to 600 timestamps. So we had to downsample that to around 40 to 50 time steps so that we do not require much processing resource or memory resource for our models. So all the methodologies that we are going to cover has this basic framework of the diagram that is presented. So we have the data set, we perform the pre-processing, then we do the feature extraction, and then we have multiple classifiers that I'm going to discuss, and finally we have the predicted class. So starting with the methodologies that we tried, first of them is the multi-class support vector machine, or SVM as popularly known. So SVM is basically a machine learning model that tries to separate classes by maximizing the distance between the classes by performing a hyperplane separation algorithm. Second, we have the random forest classifier. It is basically an ensemble method where we apply decision trees, but we do not take a single decision tree. Rather, we take a bunch of decision trees, the ensembling method. The main motive behind this being that if we have a lot of uncorrelated members in our decision classifier, then it tends to give a much correct answer. Next, we also experimented with gradient boosting classifier, which is basically a boosting scheme in which we keep on adding weak learners, and we keep on doing so until our loss function reaches a predefined threshold value. So once the objective function is satisfied, we stop the training procedure. And then we have the LSTM, or popularly known as the long short-term memory. And this was mainly done on the temporal signals. So we took the temporal EEG signals and we feed it through the LSTMs. And after that, we take the predicted class, and using a loss function of categorical cross entropy, we determined the total accuracy and trained the model the same. Then we have a multilayer perceptron model on statistical features. So all the methodologies that I discussed so far used directly the time signals. But in this procedure, we used statistical feature extraction in which we took the mean, median modes, standard deviations, skewness, kurtosis, maxima, minima of segments. By segments, I mean if you have a length of EEG signal, we subdivided that signal into smaller subbands or segments of say 4 segments, and then we took the statistical features of those segments as well. So this provides a statistical representation of those signals. Then on the extracted features, we apply a multilayer perceptron model, also known as the ANN, or fully connected networks, and we perform the classification task. And apart from that, we also experimented with the one-dimensional convolutional neural network. So the main difference between 1D convolutional neural network and the normal two-dimensional ones is that in 1D convolutional neural network, we use one-dimensional kernels instead of two-dimensional kernels. Since we used the EEG signals that had temporal representation over time, the amplitudes presented a one-dimensional signal. So we could also experiment with this method. Then we also opted for a method that was known as a connectivity matrix method. So what this method does is that we try to find the correlation between the signals obtained from different electrodes, like the intercorrelation between the intracorrelation between the signals. So this is connectivity matrix is basically obtained by measuring the relative information between each of the electrode sequences. The equation that describes this is that relative information is the KL divergence between the joint probability distribution of two variables and the independent probability distribution of the two variables. Or we can also say that the relative information between any two sequence or any two probability distribution is mainly the amount of uncertainty that is reduced regarding a random variable on observing another random variable. So when we find the relative information of one sequence with respect to another, and we do this for 4 electrodes, so we get a 4x4 connectivity matrix. So this was the representation that we used to train a classifier, mainly a 2-dimensional CNN, and we also yielded a result from this method. Finally, we come to the method that yielded the best performance, and this is the main proposed methodology that we do in this paper, and it is the discrete wavelet transform. So firstly, I would like to explain a bit about discrete wavelet transform. Normally, the signals that we obtain from EEG are temporal signals. So people often does that we take the power spectral density or we take the frequency domain representation of the signal. But we often do not observe that if we do a Fourier transform of a temporal signal, then we might lose the temporal localization information of the signal, like which frequency component occurred at which time instant. So for that, we require a representation that incorporates both time and frequency and the amplitude. So discrete wavelet transform is basically another case of continuous wavelet transform. So the mother transform is basically wavelet transform, the generalized one being the continuous one, and this is the discrete version of it. And the schematic for discrete wavelet transformation has been shown on the top left, where we can see that a signal is decomposed recursively into two different pipelines. One is the low frequency component, another is the high frequency component. The linguistics that goes with this is that the low frequency components are known as the approximation coefficients, and the high frequency components are known as the detail coefficients. So at every level of decomposition, we separate the detail coefficients, and as we progress through the pipeline, we downsample the sequence by a factor of 2. So we basically half the sequence length every time we traverse this pipeline. And the mathematical representation of the same working is represented on the right of the screen. And below we can see that for a single example of EEG, we can see the representation of discrete wavelet transform. The graph represents the time frequency representation. On this obtained time frequency representation, which are basically 2D images, we cascaded the images along the channel axis. So it yielded a 4-channel image. And on this image, we applied a convolutional neural network, a 2-dimensional convolutional neural network. And this model was trained from scratch, like we didn't use any pre-trained models. And we finally used the experimental setup. So the experimental setup was basically a 5-fold cross-validation method in which we split the dataset into 5 different folds. So in each iteration of the folds, we use one fold as the validation fold and the rest of the folds as the training fold. So the main motive behind using the 5-fold cross-validation is that it provides a very robust estimation of your model's performance. So you may say that the model is not biased towards the training and validation dataset, provided it might happen that maybe the validation fold contains an outlier sample, or maybe the training fold contains an outlier sample. So the model won't be biased towards that. We will shuffle the dataset according to the iterations, and we get a very good estimation. Coming to the result, the state-of-the-art result that has been proposed so far is 31.35%. The dataset that we used actually had a lot of redundant samples. So getting the result on this dataset was something that is quite tricky. Most other works do not address this dataset, so we picked up this one in order to address some of the problems associated with the noisy EEG datasets. So we achieved a result that is almost 3% higher than the state-of-the-art result, and the ablation study provides all the results that we obtained with the other methodologies that we used. So we can see that the best performance is obtained by the 2-dimensional convolutional neural network on the discrete wavelet transform features. We even tried the 3-dimensional convolutional neural network, but it performed a bit less well than the 2-dimensional one. And apart from that, we have the SVC, random forest gradient boost, LSTM, the DNN or the dense neural network with statistical features, 1D convolution. We also used random forest on the connectivity matrix, and also used convolution 2D, as I said before, on the connectivity matrix, and also ANN or the dense neural network on the connectivity matrix. And the best of all is obtained in the convolutional 2D on discrete wavelet transform features. Coming to the analysis, which is also a major part of this work, is that we found that whenever we are using a dataset that contains a lot of redundant samples, like if I go back to the slide where I showed the dataset composition, we can see that there are almost 11,000 samples that belong to the redundant class. This class doesn't actually represent any digits. So the model almost got very confused with this redundant class. However, we also see another thing is that on the right, we can see some of the EEG signals in visual form. And these 4 samples actually belong to a single class of class 0. And the main point of putting up this picture is that we can see even for a single class, class 0, the temporal representation of the signal is quite varied. So it is even hard for a human to decipher from these signals whether the person who is giving the EEG signals is actually thinking of a single class or multiple classes. Apart from that, we also understand that the information encoded in EEG signals are quite subject to mental state variability. So this thing actually incorporates the point that whenever we are doing an experiment in EEG recordings, we have to consider the fact that a person's mental state is biased towards the context state, or should I say the past state of that person. Say the person is not in a good mood that day. Say the person made an accident that day, or maybe he was too much happy than normal that day. So even that is going to affect a bit on the information encoding of the EEG. So this mental state variability poses a very big problem to the EEG recordings and the ground truth levels that we associate with them. And apart from that, we obviously have the instrumentational noise, which mainly comes from electromagnetic noise and also from skin conductance variability. So electromagnetic noise often comes from the places like if someone is very much near to a radio wave transmitter, like a cellular network tower, or maybe any other radio devices that uses radio frequency. Even that might cause a problem because the EEG electrodes might pick those electromagnetic noise as like a antenna does. And apart from that, the skin conductance variability also plays a major role because every person has a different amount of resistance or impedance associated with their skin. So the device that we are using on that person's scalp has to do a lot with the resistance of their skin or the amplitude that we record from that person. So lastly, we conclude that there is a weak correlation between the signals for the same, as I started with the point, as we see on the right, that even of the same class, we do not get a very straightforward representation even in the time domain. Obviously, we could work to the frequency domain and the feature extraction part, but we need to keep in mind that even a machine also has to take this into view, that if a human being is unable to understand the difference between two features, then it will be obviously hard for a machine learning algorithm also to cope up with the difference of the signals. All right, then I would like to conclude the presentation by saying that even though there are a lot of problems associated with this EEG techniques, there are a lot of potential that we are going to entertain in the future. The most important of them being the driver attention monitoring, one which we saw in the keynote speech in the beginning. Then we have control of ground-borne, airborne vehicles, also one that was mentioned in the keynote speech. Observing animal sentiments. This was yet another innovative idea that has been discussed in the literature recently, that says that we can use EEG signals for animal sentiments. So maybe the day is not far when we will be able to communicate with our pets using EEG headbands, a non-invasive method. And again, coming to the communicating with coma patients, as I said earlier, that coma patients, say someone family member who are like in coma for years. So a methodology that could help them to communicate with their family or with the medical personnel would be a lot of help to those people. So EEG might come to a lot of help to those kind of situations. And lastly, but not the least, mental health monitoring. So we have to accept this fact that this century is going through a lot of mental health depression and other kinds of mental health traumas and other problems. So if this kind of problems could be could be monitored actually through this kind of non-invasive methods, then this would actually pave our way to a much more healthier world in which everybody could like get cured of mental diseases, and they could live a very much happier life. So yes, that's pretty much it, and I'd like to take any question. Thank you.
Thank you very much.
Thank you, Nicola.
It's my pleasure to make an oral presentation at ICPRAI 2020 today. My topic is Generative Adversarial Synergetic Networks for Anomaly Detection. I'm reporter Li Chaobo, and my supervisor is Li Hongjun. I've divided my presentation into 5 parts. As we all know, anomalies are happening frequently in public areas, such as hospital areas, sports, and so on. The manual monitoring or playing back to view are required in real life, which takes lots of time and efforts. So anomaly detection is an important aspect of intelligent video surveillance. The related work of anomaly detection mainly based on traditional method and deep learning method. Traditional methods usually include support vector machine, Gaussian transformer, and others. Research studying or deep learning for anomaly detection has proposed alternative approaches to enhance the ability of feature extracts such as auto-encoder and generative adversarial net. Before the proposed method, let me introduce the generative adversarial nets briefly. It consists of generator and discriminator. The generator with noise input is used to obtain the distribution from real data and generates the new images. The discriminator judges whether the input data is from real and the generated data. They are trained by the discussing min-max scheme. Why did we conduct this research? Anomaly is irregular, diverse, and unpredictable. It is almost infeasible to gather all kinds of anomalies to tackle the problem with a classification method. It is not always possible to generate samples directly for improved performance. The constraint method mainly trains networks using normal data to avoid the definition of anomaly. However, there are 2 situations. One is the anomaly are distorted and the normal image are reconstructed inadequately. The other is the normal samples can be reconstructed well, but anomaly can be reconstructed roughly. Therefore, it is not accuracy to judge the anomaly according to reconstruction error. Inspired by a cooperation machine, we proposed the generative adversarial synergetic networks for anomaly detection. It consists of synergetic generative networks and the adversarial discriminator networks. The generator is the important hub of the 2 subject networks. The discriminator acts as a detector, while the promoter facilitates the other modules to extract the key and discriminate features. The 3 modules supervise and promote each other. We will present 2 subnetworks in details. First, let's look at the adversarial discriminant network. It is designed to discriminate the normal and abnormal attributes to the unknown data. There are generator and the discriminator, improving each other through adversarial learning. For generator, it takes the noisy patches as input and outputs the generated patches. For discriminator, the input are both generated patches and the real patches. Then the probability scores of each patches are obtained and fed back to generator. Next, The generated patterns are incompletely subjected to descript if only rely on the discriminator to constrain generator. We further use the synergetic generative and networks to generate patterns and compile the distribution. The generator and the promoter are built through synergetic learning. The promoter takes noisy and the generated patterns as input. Objective function. It is important to train networks. The discriminator wants maximizing objective function. The promoter always trusts the ability of generators, so the purpose of generator and promoter are minimize the objective function. We show the flowchart of generative adversarial synergetic networks for anomaly detection. The structure of discriminator and promoter is similar. The convolutional layers of generator are less because of reductancy and inference information images. The number of feature maps between the convolution and the deconvolution is not symmetrical. It is necessary to consider the optimization after building the networks. The overall optimization is shown. We evaluate our method or typical UCSD-PD2 and the experimental results and are analyzed in detail. This figure shows the part of abnormal and normal patterns. It is evident the generated patterns is no noise. The anomaly is distorted while the normal subject can be reconstructed better by proposed method than in reference 1. We use the difference of probability scores to distinguish the normal and abnormal samples. The probability scores of first 31 normal samples are relatively larger, while the later abnormal frames are relatively smaller. We compare our proposed method with other algorithms or AUC and EER results. In conclusion, focus on the anomaly detection. We propose the generative adversarial synergetic networks. We find the combination of adversarial synergetic idea can improve the discriminability in which the two objective functions of optimization are taken to extract the discriminant features. In feature work, key features such as the correlation between video frames and the speed of abnormal behavior are considered. In addition, the performance can be further improved by designing more excellent and balanced networks. The combination between anomaly detection and sense analysis can be considered. Thank you for your attention. If you have any questions, don't hesitate to contact us.
Good morning, experts and students. It's my pleasure to make an oral presentation at ICPRAI 2020. I'm Suen and my supervisor is Hongjun. I will share the paper is much features integration for speech emotion recognition. Next, I will elaborate on this paper from 5 aspects, which are background, related work, methodology, simulation results, and a summary. The first is the topic selection background. Speech emotion recognition has been widely used in the field of human-computer interaction, such as education field, medical field, service field, and so on. At the same time, speech emotion recognition is also an important and challenging speech recognition technology. Next is the related work. To release a speech emotion recognition, substantial research work on recognition model have been proposed. For example, traditional algorithms, Handwritten model, cross mixture model, and so on, where traditional networks usually extract the time domain information of the input speech, and deep learning algorithms proposed in recent years, such as convolutional neural networks, long short-term memory, and so on, where deep networks usually take the spectrum of the speech as input. We mainly use the proposed method to extract MFCC features and other statistical features, such as fundamental frequency, short energy, and so on. The third is our methodology. And figure 1 is our algorithm framework. The MFCC features are directly transformed from the orange speech. Then speech groups are related to figure the correlations between features, extracting the discriminative features. After that, we map features to nonlinear features and enhance its independence. Finally, the multi-features integration are sent to the output layer for calculating the output weights. In order to extract the emotion features of speech, we mainly take 3 steps. The first is speech features extraction. And the second is to adapt space groups to extract the discriminative features, where we are the MFCC features. They are the extract discriminative features by the absolute space group, and the omega ER, beta ER are the space widths and offsets respectively. Then we define the discriminative as ZG. Finally, we try to map these features into a nonlinear space by using an orthogonal matrix, the vectors in which are independent and orthogonal, where each are the nonlinear features. Then calculate the derivation of omega, where lambda is a positive quotient and I is an identity matrix. The fourth part mainly explains our experimental results. The speech data set used in this paper is CSRA Chinese Emotion Corpus recorded by the Institute of Automation Chinese Academy of Science, which is recorded by 4 people in a clean recording environment. Table 1 compares with DNSVM and CNN. It can be from Table 1 that our algorithms perform better than DNSVM and CNN, regardless recognition accuracy and train time consuming. In order to verify the importance of multi-features integration, we perform the following experiments. And figure 2 shows that the integration of multiple features is more effective for emotion recognition based on speech. Moreover, in order to explore which type of features in this paper contribute greater to emotion recognition, we conducted the following experiments, and the experimental results are shown in Figure 3. It can be seen from Figure 3 that if the nonlinear features, the discriminative features and the MFCC features are respectively missing. The MFCC features have more contribution to recognition emotion. The last part is summary. One MFCC features contribute more to recognition rate and spend more time on featuring as well. 2. All our method has a center improvement in the loss of train time. Its accuracy needs to be further improved. 3. We will explore features that are more generalized and future improve the recognition accuracy on speech itself with more emotion. Thanks.
My name is Cheng-Yuan. Today I would like to present my paper, A Deep Object Detection Method for Pineapple Fruit and Flower Recognition in Cluttered Background. First of all, please allow me to introduce myself and the lab. I'm a PhD student from Beihang University. My research interests include computer vision, 3D reconstruction, and object detection. The School of Computer Science and Engineering has 2 state key laboratories, namely the State Key Laboratory of Software Development and the State Key Laboratory of Virtual Reality. Besides, the major of Computer Science and Technology and Software Engineering was selected into the National First-Class Construction Disciplines. Our team belongs to the State Key Laboratory of Software Development. The leader of our team is Professor Xiaobai, whose research interests are computer vision, pattern recognition, machine learning, half-spectral image processing, and remote sensing image analysis. Our group has 1 professor, 2 associate professors, 6 PhD students, and 15 master students. Besides, we have close cooperation with famous laboratories abroad, such as Professor Edward Hancock's team from University of York and Professor Jun Zhou's team from Griffith University. This work was finished during my visit to Professor Jun Zhou's lab. The pineapple is a popular product of Australia, as the nature initiation is not synchronized. Fruiting can be spread out over 2 or 3 months, leading to lots of small harvest runs with high human labor and financial costs. So currently, farmers make decisions based on experience. And there's no technology available for suitable estimation of flowers and fruits to support a current estimation of profit margin for each harvest round. So in practice, efficient harvest planning needs a sophisticated detection of return in order to overcome challenges such as insufficient or over-illumination, heavy occlusion, variation of growing stage and fruit size, and camera viewpoint, and so on. In this work, we present a CEN model for a current pineapple fruit and flower recognition using a state-of-the-art deep learning-based object detector, ULO-V3 model. Yeah, we collected real images from pineapple orchard using digital cameras mounted on different platforms. Then we selected suitable images and manually annotated them with ground truth bounding boxes to create a dataset. The network takes RGB images as input and outputs bounding boxes and object label for each bounding box. In this work, we mainly concentrate on two classes, the fruit and flower of pineapple. Yeah, when training the network, we follow the loss function of ULO-V3 model. The whole loss function is a weighted sum of three loss functions, namely the objectness, confidence loss, the classification loss, and the coordinate regression loss. The model was trained on a single NVIDIA GPU with 2 images per mini batch. Our model was pre-trained on COCO dataset and then refined on the dataset we collected. For all experiments, we set hyperparameter lambda 1, 2, 3 as 1. 3 cameras were used to collect data in different imaging settings from a pineapple orchard in Australia during November to December. The imaging process considers scales, illuminations, and viewpoints. Camera 1 took images from the top of pineapples in close range, obtaining images with detailed features. Camera 2 and 3 were mounted on the spray broom, taking pictures from a bird's view. We selected a total of 200 images to form the dataset, and then manually annotated each image. There were totally 786 bounding boxes for fruits and 2020 bounding boxes for flowers. In the experiments, we divided them into 3 groups, 140 images for training, 30 images for validation, and the rest 30 images for testing. So we used the 4 evaluation criteria to assess the performance of the proposed method, including precision, recall, MAP, and F1. The average MAP and F1 score of 2 classes are 0.64 and 0.69. And we also visualized the bounding boxes of the ULO-V3 model. We can see that the model obtains the permission detection performance and various illumination conditions, object sizes, viewpoints, and heavy occlusions. And we also show some wrong detections. When there are other objects with similar color or shape with pineapple, the model is prone to false detection. For pineapple, the process from flowering to fruiting is gradual. This results in late-stage flowers that are very similar to early-stage fruits. Therefore, the flowers may be misidentified as fruits or vice versa. So in the next step, we plan to collect more data to train the network models and develop them to automated equipment. And that's all. Thank you.
Thank you very much. That's very nice presentations. We thank all the presenters for your excellent presentations. For the next keynote speech by Ms. Sheila Low, we'll take a 10-minute break before. And I would like to share the screen to introduce Sheila to you. Sheila Low is the president of American Handwriting Analysis Foundation and a board member of the Forensic Examiners. She is the author of 15 internationally acclaimed books dealing with handwriting and personality. So in one of her books related to handwriting analysis of famous and infamous people, including the royalties, presidents, and so on, including President Trump's handwriting, she made some comments about his handwriting. And she's also a court-qualified forensic handwriting expert. Very good. So now we will have the keynote speech by Sheila Low, a well-known expert in forensic science and handwriting analysis. She is the president of the American Society on Handwriting Analysis and has written more than 15 books. And one of the books, she analyzed the handwriting of famous and infamous people, including royalties, presidents, and so on. And I also read her talk, in the book related to the analysis of President Trump's handwriting. So let us listen to Sheila and welcome to the talk to everybody. Sheila.
Thank you very much. It's a great honor to be invited to make a presentation, so I appreciate it. And I'm going to be talking about handwriting and the patterns that we see in handwriting. And nobody knows better than you that patterns can be found everywhere in life, and they exist in all natural things. Even there are rhythmic patterns in the ocean waves and in spirals in plant life, the light and dark patterns on the coat of a zebra. There are patterns in music and math and dance, even in a golf swing. And patterns are found in handwriting, which is why it's possible to determine who wrote something. Because just in the same way that nobody shares fingerprints, nobody shares the exact same handwriting. In fact, this is the basis of two major axioms in document examination and why we can authenticate handwriting. Because no two people write exactly alike, as in their signature particularly, and no individual signs their name exactly the same way twice. Only a machine could do that. And people are not machines. We're not robots. So everyone has a personal range of variation in the way they sign their name. Some people write their name over time in a very similar way every time, but it's not going to be exact. Other people have a wide range of variation. So let's talk a moment about signatures. What is a signature? It doesn't have to be your first name and your last name. It might be a symbol. Like down here in the bottom left-hand corner is a cruise ship captain. His signature looks like a ship on water. You wouldn't know that this name is Demetrius Milonas because he uses a symbol as his name. Or it could be a graceful logo like the one up here near the top of the actress Angelina Jolie. It's illegible, but it's a symbol of who she is. It represents herself. And down here we have Brad Pitt, the actor, whose signature is like a symbol. It kind of looks like a sword. This one is Serena Williams, the tennis star, and you can see the symbol of her jumping up to hit the tennis ball. We have down here a World War I ace fighter pilot named Valentin Gebhardt, and you can see the little airplane and his signature, and you see the wings in the front of the plane. And others. On the bottom right, this is the signature of a man named John Bobbitt, and you see in his signature a butcher knife, which makes sense because his wife used a butcher knife to cut off his penis. So a signature can be many different things, but it symbolizes who the person is. Now, a signature is just it's like the cover on a book. It's what the person wants to project to the world, what they want you to see. Over here we have Martha Stewart, the entrepreneur, who writes her name very clear and open, so there's like nothing to hide. But as I've said, nobody writes their signature the same way exactly twice. And so if you look at these seashells, they're all the same shell, the same type of shell, but the color and the way the patterns are displayed can be somewhat different. None of them is exactly alike, and that's how it is with signatures. Everyone who writes has a personal range of variation. Now, a signature, if you're famous enough, may become an autograph. And it's quite clear that in these three cases, these three sets of signatures, that the same person wrote each set, because even though they're not exactly alike, the patterns in them are. On the left, these three signatures were written by Angela Merkel, the Chancellor of Germany. And she writes a very fast signature with few details. Her name is illegible, but it's consistent within her natural range of variation, not a machine. You can see, though, it's the same person. So personality-wise, your signature is your public image. The rest of your handwriting shows the truth about yourself. Her signature, Merkel's signature, shows her to be a very quick, intuitive thinker who doesn't reveal very much about what she's thinking. In the middle, we have Donald Trump, and his signature is consistently full of dark, heavy angles. Plus, notice how he brings the last stroke of his name from the P, slashing back through his name. His signature, among other things, reveals aggression and a great deal of pride, but also self-destructive tendencies, because when you slash through your signature in any way, and your signature represents yourself, it's a self-destructive act. Now, it's interesting that his signature, Trump's signature, is very different from the rest of his handwriting. So what he projects to the world may not be entirely what he is inside. On the right side, we have Barack Obama. And President Obama, like Merkel, has a highly simplified signature that is not easily read. It's illegible. The tall capitals show a lot of pride. It shows intuitive thinking and reaching up for high ambition. But in his case, the final stroke is very long and it has a hook in it, which in effect holds people away, because there's a lot of symbolism in handwriting. This long ending stroke keeps people from getting too close, and there's a self-protectiveness in the way the first name goes into the second name. Now notice that the fourth signature in this group is somewhat different from the others. And when I looked at it, I thought it must not be genuine because it's so slow and halting. In handwriting authentication, there's another axiom, and that is if two or more signatures are written by the same person but they look different, there must be a difference. There must be a reason for the differences. And in this case, I found out that when President Obama signed legislation, he would use about 6 different pens. So he would write a little bit of the signature and then switch pens and write another bit and then switch again. And then at the end, he would make a presentation of those pens to people who were involved in the legislation. Now, in handwriting, there are three general factors that can affect handwriting and disrupt the patterns. The first group of factors is the mechanical. That would include the writing materials, your pen and paper. For instance, Donald Trump uses this very heavy felt tip pen almost all the time. And if he was to write on a very porous paper, that handwriting would look very different than if he wrote with a fine tip pen on a slick paper. The writing surface makes a difference. If you're writing on a desk, the writing will look different than if you had, say, a magazine on your lap, sitting in bed with the magazine on your knees. Or if you were writing on a wood surface with a lot of ridges, that would affect the writing. Also, your writing position. Again, sitting up in bed or holding a paper on somebody's back while you sign something, that will affect your handwriting. If you are ill and too weak to be able to hold a pen and write, you might, if you needed to sign a document, you might need someone to guide your hand. So they would actually hold your hand and help you sign. But when that happens, the person who's guiding your hand doesn't know why you write the way you do, and so there will be some influence from their own writing patterns. The same is true if you were coerced into signing something. The unwillingness to sign would show up. Now, the next group of factors are physical. These would be things like your age, your state of health, your eyesight. If you'd had an injury, for instance, if you have a shoulder injury or a wrist injury, that is going to obviously affect your handwriting. And handwriting will change over age. Illness will have an effect in some instances. For instance, Parkinson's, we have what's called micrographia, where the handwriting gets very tiny. And if you're tired, that can have an effect on your handwriting too. Also, chemicals, and we're going to see some examples of handwriting after alcohol use and recreational drugs. Some medications will affect handwriting. Your hand-to-eye coordination, if you're clumsy or if you're impaired in some way, that will affect it. And mental status, somebody who has a low intellect is going to write slower than somebody who is quicker in their thinking. And somebody just pointed out to me yesterday an important one today, and that is lack of practice. These days, we spend most of our time keyboarding, and so that is going to have an effect on handwriting. Now, here is an example of handwriting under the influence of alcohol. Some years ago, the House of Seagram's Liquor Company did an experiment, and they would give, here's the beginning at the party, they would take a handwriting sample, and then after 2 drinks, 4 drinks, 5 drinks, you can see the loss of control, and after 7 drinks, the person has no control over the pen. So the message was, if you can't even control the pen, how are you going to control the car? So drinking and driving is not a good idea. You see how the patterns are disrupted, although the basic pattern stays the same. This is the effect of heroin on handwriting. And over here on the right, we see a handwriting under the influence of cocaine, and at the bottom, alcohol. Now, not all handwritings are going to look like these under the influence, but this is just an example. And this one on the bottom of the alcoholic is an attorney who would go to court in this condition, very drunk, and yet he was able to win 6 very important death penalty cases. But on the inside, we see from his handwriting what was going on. Here is two examples of the effects of dementia on handwriting. And you can see again how the handwriting is falling apart. The patterns are unable to be maintained. And now here's an instance of cancer. These three letter J's show the pen stroke, how the pen stroke under strong magnification shows how the ink line, which is called the ductus, is in the early stages of cancer and how it deteriorates over the years. And here's an actual example in handwriting. In this case, the person was healthy. But here, over a year, we see again the deterioration, and finally, just prior to her death, the complete loss of control and the effects on the actual stroke. Now, the third group of factors that affect handwriting are psychological and personality. Excuse me a moment. Personality is just one of the things that affects handwriting. Your mood, if you're excited or angry or happy, your handwriting tends to get larger. If you are patient or impatient, it will see the effect in the speed. If you're depressed, your handwriting may get smaller. And if you have personality disorders, such as OCD, that's going to be different from a handwriting of a person who is diagnosed with bipolar or schizoid disorder or one of the other personality or anxiety disorders. So here are a few examples of handwriting styles in different languages. And everybody writes differently, so it would be impossible for me to show you all of the various types of handwriting. Excuse me. But here we have two great human rights activists. On the left is Nelson Mandela, and the one in the middle is Elie Wiesel. And so let's look at some other handwritings of people who are not good people, not on the level of these social activists. These are criminals. The one on the left top is a female serial killer, and on the bottom right, a male serial killer. On the bottom left, this is Ken Lay of Enron, who was an embezzler who stole the money from their investors. And on the top right is Saddam Hussein, a dictator. And you can see very different types of patterns from what we saw in the last group of samples. Now, let's go backwards for a little bit and see how handwriting develops. Every country in the world has its own school model or copybook. This is the style that's taught to the children, usually in around the 3rd grade. And the major ones that have been taught in the United States over the past century or so are the Palmer method, the Zehner-Blosser, which was even earlier than Palmer, and in 1980 the Danielian was introduced. And the difference between the Danielian and these other two is that it's much more simplified. It doesn't take as long to write. There's not all the elaborate little curlicues. So it's a nice, simpler version. And there are others, but these are the chief ones. Now, there are newer ones being taught. And two that I like are the New American Cursive and Cursive Logic, which are also simplified. They're less time-consuming than some of the old models. But regardless of whether you're taught to write in an English style or a more pictographic language or Hebrew or Arabic or Cyrillic, when the children go to school and learn to write, they're all taught to write the same patterns, and they go through the same stages of learning, which is the first thing you learn is to write individual letters. So you're writing in letter impulse once you've got those letters understood. And when you know what you're writing, you can string them together in word impulse. So you're writing a whole word at a time. And finally, when you're comfortable with that, you're writing in sentence impulse, stringing whole sentences together. And when the child is comfortable with writing, it begins to individualize and maybe cut off some of the extra loops or cut off the initial strokes on letters or the final strokes. He may simplify it or go to the other extreme and add embellishments and make it more fancy according to his or her personality. So at that point, we say the child has reached graphic maturity, which simply means he knows how to write. And there we have what we call master patterns for each letter. You see here that we have 3 different styles of the letter A. And it may be that this person uses one style for the beginnings of words, another style in the middle, and another style at the end. And altogether, we say that those are the master pattern for that letter. And of course, they have a master pattern for each letter. So overall, the master pattern is the way that the person writes his or her particular letters with natural variations, because nobody writes like a machine. When it comes to personality assessment through handwriting, we look at 3 big pictures. We're not looking, at least the style of handwriting analysis that I do is called Gestalt, and it looks at the whole writing, not just the individual pieces of it. We look at space, form, and movement. Space comes first because you have to have a frame in which to place the handwriting. And for our purposes, that frame is a piece of paper. The writing is arranged on the paper in a way that we're looking at the amount of space that's left between the letters, the words, the lines, and how much space is left around them in the margins. So a well-arranged page says something very different than one where the writing is crammed together. This top left writing is well arranged. There are reasonable amount of space between the letters, the words, and the lines, and it has a nice margin around it. The one on the bottom right, however, is all crammed together. There's no space at all, no airspace. And of course, in this few minutes, I can't teach what all those things mean, but just be aware of what we're looking at. This top right handwriting has a lot of very wide spaces between the writings. And I'll just say that somebody who writes with very wide spaces is less emotional and sociable than somebody who, like on the bottom left, who writes very close together. It's not as jammed together as the one on the right, but they're very close and much more emotional and sociable. The spatial arrangement on the page is the most unconscious aspect of handwriting. And once we've learned to write and we develop our own idiosyncratic writing habits within the confines of that piece of paper, the movement of the pen creates a second component, and we call that movement. Well, if you put your pen down on a page, all you get is just a dot. Nothing happens until the pen begins to move and create patterns of movement. I mean, we can infer some things from that dot, the size, the placement, the shape, but we really need movement to know more about the writer. So you're seeing here an example of my writing and my patterns. This is just one type of movement. There are countless others, but the pen must move. And here are some examples of different kinds of movement. We have a very fast dynamic writing here on the top left, and on the bottom left, a very slow writing of an adult. But you can see that it's quite different. On the top right is copybook writing, just like she learned in school. And here we have two examples of printing. So these are representative of very different personality styles. And just as you watch, you know something about someone when you see them walk. For instance, do they take big, confident strides or very small, timid steps? In the same way, the various personality types are reflected in the movement, and we can view movement on a continuum. In handwriting, we're looking for a balance between contraction and release. So, oops, let's go back again. On the extreme left of the continuum is extreme contraction. This is a painful handwriting to look at. It's so squeezed together. It's like an accordion that's been squeezed. And a contracted writing is going to look very linear, like this, but this is an extreme. Here's a less extreme contracted writing. You can see the letters are still very narrow. It's contracted, it holds back. In the middle is a balanced writing, where there's a balance between letting go and holding back. Here's a more released writing. This one has no rhythm in it, but it's released because there's less control. Release is about control. And here's an extreme release. Because it's very rounded and there's basically no straight strokes in it. What we want is always a balance. Now the movement in the space, we have the space and then we have the movement within the space, and the movement in the writing creates a third element of writing, which is called form, and that's the way the writing looks. And these are all very different styles of form. Here's one that's quite elaborate. It's got big loops and it's carefully written. It's got long T-bars. This one is quite simplified, cut off loops. We have a more copybook style here. And here we have a block printing of an architect. And here is a more artistic writing. So you see how form is the most conscious aspect of writing, because it is the style the writer chooses to represent himself or herself. And really we haven't come close to scratching the surface of why handwriting reveals personality. But hopefully my presentation has given you a tiny inkling. And if you're interested in learning more, some of my books here are on, well, all of my books are on Amazon, and they're in ebook and print, and I have a self-study program that you could read about on my website. So at this point, if anyone has any questions, I would be happy to answer them.
Thank you very much, Sheila. So the floor is open for questions or comments.
Hello.
Najla has a question.
Hello.
Yes.
Actually, I want to ask about, you said that we can know the age of the writer from the handwriting, but no?
No. Age is not something that you can tell. You can tell their degree of emotional maturity, but not their actual age.
Oh, okay. Then I have no question now. Okay, thank you very much.
All right. Yeah, there are some things, the things that you cannot tell from handwriting conclusively are age, gender. You can see whether the person has more traditionally male or female characteristics, but not their actual gender. Age, gender, and which hand they write with. And you can't tell the future, but you can tell a lot about the past.
Okay, thank you very much. Thank you.
Sure, thank you.
Well, Najla just gave a talk related to gender, right?
Actually, we have done some experiments with the computer to extract the gender, and we got a high recognition rate actually. And we applied some deep learning techniques and some machine learning techniques on the handwriting to extract the gender, and we got a good recognition rate.
Excellent. I'd be to hear more.
Yeah, this is one of my contribution for my PhD thesis actually.
Wonderful.
Yeah.
Please keep me posted on that.
Yeah. Thank you.
I mean, it would be
other questions, comments?
It will be interesting to see against a human, because there are some handwritings that just looking at them looks, for instance, very feminine or very masculine, but they're not. They're the opposite gender. So I'd like to know how the computer would interpret that.
Any other questions? If not, I would like to thank Sheila very much.
Thank you.
So this is the end of today's sessions. Thank you very much. Bye-bye.